In this video, I'm going to be talking about the ways in which we can so-called multiply vectors. More commonly, these are referred to as vector products. I'm going to be highlighting the main ideas from section 1.10 of your textbook. So if you're comfortable with these ideas already from previous math exposure, then this video is probably not necessary, but it will highlight some of the conceptual understanding of the vector products that we'll use later in this course and more in 2049. Okay, so the first kind is going to be what's called a scalar product. And the reason that it's called a scalar product is because the result of this product is actually a scalar and not a vector. And the scalar product is also known as the dot product. And the reason it has that name is because the symbol for it is a dot. So the way that it works is that we have A dot B, so that's how it's referred to, A dot B, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between A and B. So again, this phi is the angle between vector A and vector B, and these are the magnitudes. And if we try to understand this conceptually, then what we can see is that it's actually taking the parallel component of one of the vectors, basically the projection of one of the vectors onto the other one, and then multiplying that together. So as an example, let's say that our vector B is at some angle relative to vector A, and that the angle between them is that angle phi. So if we look here, then the scalar product, A dot B, is equal to the magnitude of A times B cosine phi. And B cosine phi, right, if we look at this right triangle here, is simply going to be equal to the projection of B along A, the component of B that is parallel to A. So this would be here B cosine phi. So what this does is the scalar product takes the component of one vector, let's say B, that's parallel to A, and then multiplies. It actually works the same way. You could interchange A and B and make the same case that you're actually taking the component of A that's parallel to B and then multiplying. It depends on the situation, which interpretation you use. Obviously, which one you call A and B is not important, and that you could just as easily take the projection of A along B and end up with the same result. So this is one way in which you can calculate the scalar product. When you do know what the angle between them is and you can figure out their magnitudes, then it's quite simple. It ends up having no direction. It is a scalar, so there's no direction. It's just a scalar. But if you don't know it in their magnitude and direction components, and you only say no, their unit vector components, then you can actually calculate A dot B in another way, which is that it's simply going to be equal to the x components multiplied together, added to the y components multiplied together. And the math and the derivation for that is shown in section 1.10. But the result is that A dot B is equal to AX times BX plus AY times BY. So you have then these two methods which allow you to calculate the scalar product between two vectors. And given the situation, then you can choose which one makes more sense. Now, what I'll say about this at this point is that we come back to the dot product in chapter 6. when we begin to talk about the idea of work. All right, so that's the overview of the main ideas for the scalar product. And now we're going to talk about the second kind of way of multiplying vectors, which, if you might guess what it is actually going to be called a vector product, where the result is a vector. And instead of taking the parallel components of the two vectors and multiplying them together, it's going to take the perpendicular components. All right, so let's go ahead and write that out. So here we can say that we have the next kind is called the vector product. And the vector product is also called the cross product. And the reason it has called a cross product is because, again, that's the symbol. So this is what it ends up being, and then that's the symbol, and both of those are commonly used. All right, so first let's talk about the result is a vector. So if we remember, right, that simply means that it's going to have a magnitude and a direction. Now with the vector product, in order to discuss it, we have to talk about the magnitude and the direction separately. So the magnitude of the vector product, which we can write as A cross B, so that's again how it's referred to, A cross B, and then magnitude, those symbols there, is actually going to be equal to the magnitude of A times the magnitude of B times the sine of the angle between them. So it's actually not very different than our description previously for the scalar product, where you had, it was the cosine of the angles between them. So for the magnitude of the vector product, it's simply now the sine of the angles between them. And again, I'll write down here that this is the angle between A and B. So sometimes the problem doesn't necessarily give you the angle between A and B, but then you need to figure out what it is. So if we again take these same vectors, where I had B drawn at some angle phi to vector A, then we can see that B sine phi, with this right triangle again, is actually just this component that is now perpendicular to A. So B sine phi is the component of B that's perpendicular to A. And so that component of B perpendicular to A is then multiplied by A, by the magnitude of A. So now you're taking not the projection of B along A, but the component of B that's perpendicular to A, and then multiplying those two together to get that magnitude. All right, so what I'll say then about the direction, there's a way to calculate this with the unit vector components. I'll leave that to you in chapter 1.10, although that way is not commonly used at this level of physics for 2048-49, so we won't focus on it too heavily. For the direction, however, we will use that, and you'll use it a lot more in 2049 than we will in 2048. So for the direction of this, the direction is actually going to be perpendicular to both A and B. So the final direction of the vector product is actually not going to be in the plane that A and B make. So in this case, it would be out or into the page. It turns out that it would be out of the page, and the way that you determine that has to do with something called the right-hand rule in order to get the direction. So the right-hand rule is used to get the direction. We'll cover that more when we need it because it takes a little getting used to. And so I'll just say that we'll come back to this idea in chapter 10 when we talk about torque and angular momentum. And those ideas then actually are cross products, and we'll use the right-hand rule to calculate a direction. All right, so that concludes the discussion of multiplying vectors and highlighting only the main ideas from sections 1.10. If you have any questions, as always, let me know. Thank you.